There's a lot of latitude in how an engineer might model a system. A standard joke is that if you get 5 engineers to model a system, you'll get 5 different models. Of course, if I'm one of the engineers, you'll probably get at least 6 different models because I'll want to do the problem more than one way. This is our representation of a mathematical model of an engineering system. The device being modeled has some inputs and some outputs, and the device itself is represented as a mathematical relationship between the output and the input. The choice of inputs and outputs and the mathematics used to represent the system are usually an engineering decision, and it's based on what the engineer wants to find out about the system. The fundamental math is also, to some extent, at the discretion of the engineer. It really depends on the physics that's important to the specific problem the engineer is solving, and the approach used to model the system may change as additional data become available about the system's behavior. Some or all of the approaches I'll mention below may not be familiar. Don't worry if you don't understand the details. Those will become apparent as you take more math classes. What you want to take away from this video is that there are a variety of ways to analyze systems and that the approaches vary in their complexity and difficulty. You should also understand that there are some guidelines that allow you to decide which approach to use. Now let's talk about some of the types of models we might want to create, what physical processes they model, and the mathematics used in the models themselves. First and simplest are models of systems that either don't store energy or where the energy stored is constant. A situation like this could be where a car is moving at a constant velocity. Since the velocity is constant, the energy is constant. These systems are governed by algebraic equations. Another, more interesting class of systems is where the energy is being transferred between energy storage elements. These are called dynamic systems. For example, if you apply the brakes in your car, the kinetic energy is dissipated as heat in the brake pads. Energy is being exchanged within the system. There are several varieties of dynamic systems, and the amount of effort required to model and analyze them varies widely. The simplest type of dynamic system model is called a lumped parameters model. In these models, the energy storage elements are concentrated in certain places as lumps. For our car example, we generally don't need to worry about different parts of the car having different velocities. We can just lump the entire car into one big mass with a single velocity and get an accurate representation of the energy in the car. These types of models are governed by ordinary differential equations, in which there is only one independent variable. In general, using a lumped parameter model implies that the rate of change of the input is slow relative to how fast the system can respond. If we run our car into a brick wall, the car crumples. Different parts of the car are traveling at different speeds and we can't lump the mass all together. That means that the energy transfer is a function of 2 independent variables. Models of this type are called distributed parameters models. These types of models are governed by partial differential equations, which are considerably more difficult to deal with than ordinary differential equations. So it's desirable to use lump parameters models if at all possible. Distributed parameters models are used when the input changes faster than information can propagate through the system. There are a few other qualifiers that can affect the difficulty of the modeling and analysis of a system. These apply to all of the above systems. First, linear systems are great. Engineers much prefer to analyze linear systems over nonlinear systems. In linear systems, a plot of the relationships between any 2 dependent variables will be a straight line. In nonlinear systems, plotting dependent variables against one another may not be a straight line. Nonlinear systems are painful to analyze, so engineers tend to assume systems are linear whenever possible. This assumption is one reason that the modeling and design process is iterative. All systems are nonlinear to some extent. We generally don't know how wrong we are until we get some test data. At that point, we may need to find that we redo the analysis or the design. One final category is time-varying systems. These types of systems change their behavior as a function of time, which means that the coefficients of the governing equations will be functions of time rather than constants. This also increases the factor of difficulty in analyzing a system. Most of these system types can be mixed and matched. A lumped parameters linear system model with constant coefficients won't be too difficult to deal with, but you really don't want to get stuck with a nonlinear distributed parameter system with time-varying coefficients. If you end up having to deal with one of those, try to go on vacation or maybe pretend you're dead and hope it gets reassigned to someone else. Now let's take a look at these mathematical relationships in the context of a simple system, a slinky. If I fix the top of the slinky at the roof and displace the bottom of the slinky, this is my input. And the force in the slinky, if I choose that as my output, is just a function of the distance. It's an algebraic equation. There's no energy transmission within the system. If I suspend the slinky from one hand, and my input is the displacement at the top of the slinky, and my output is the displacement at the bottom of the slinky, I now have two energy storage elements. I have a spring that stores energy as displacement and a mass that stores kinetic energy as velocity. So I have two energy storage elements, which means this is governed by a second order differential equation. I can use a lumped parameters model because the spring is always either stretching or contracting. All parts of the spring are behaving the same at any time, and the mass down here is always going in the same direction at any given time. If I stretch the slinky this way and pluck one end, I have a wave going back and forth. Not all parts of the slinky are behaving the same way. I would have to use a distributed parameters model for this. Likewise, if I oscillate this end of the slinky in this direction, the system response is a function of both time and space. This requires a partial differential equation. It is a distributed parameter system. Modeling engineering systems is challenging, but it's super rewarding. I love being able to predict how the system is going to work and being able to tell people how to change the system to make it work better.